The inversion of matrices, or more directly, the invertibility of matrices, is an important concept in linear algebra and has many applications in fields that leverage linear algebra, such as regression analysis and regression modeling. For those of you who are more experienced in calculus or algebra, this is analogous to finding the inverse of a function. Hello, welcome back to the Quant Plus YouTube channel. Today we're going to be discussing an important formula in linear algebra and an important concept in linear algebra. So, the formula I wanted to bring to your attention is that if the determinant of some square matrix A is equal to 0, then the inverse matrix of said matrix A does not exist. So now, taking a step back to discuss invertibility, what we can think about is that if A inverse, written this way, is the inverse of some matrix A, then A inverse times A is equal to the identity matrix. Equivalent to saying, or not equivalent, but very analogous to saying F inverse of F of X is equal to 1, and we can think about this first equation here as being expressing that same relationship in terms of matrices. Let's discuss the 2x2 version of this formula. Not that it's impossible to show this in larger cases, but 2x2 is, I think, much simpler to understand and much easier to calculate. So if we define a 2x2 matrix A as following, then the determinant of this matrix A is given to us by the formula AD minus BC. And if this is equal to 0, as is implied by this formula, then, well, AD is equal to BC. And solving for, let's just say, the variable A, we get A is equal to BC over D. Well, let's plug this in. If we plug in BC over D for A, then we get to here. But notice how this BC over D term is this B term multiplied essentially by the coefficient C over D. So if we kind of leverage that idea, then taking this D term and multiplying it by C over D, then we get D times C over D. And the D's will cancel out, leaving us with the variable C, and that's this C right here. So what that's showing, or what this is demonstrating, is that this first column here is a scalar multiple of this second column here. And if that's the case, then your function is not going to be, or sorry, not your function, your matrix is not going to be invertible. Kind of the intuitive explanation for why that's the case is because if the first column is a scalar multiple of the second column, then if we treat A as some coefficient matrix, then we're going to see that there are infinite solutions to that system of equations rather than a unique solution. And for there to be an inverse of said matrix, we need it to be a unique inverse. Let's give a more concrete example of why a matrix where one column is a scalar multiple of another is not invertible. Okay? So let's consider this matrix as a relatively simple example. Well, if we treat this matrix as a coefficient matrix, or our starting matrix, and our almost like our solutions, right? Our solution set as being the identity matrix, then we can perform transformations on our starting matrix, apply those same transformations on our identity matrix, and that's how we, in theory, would be able to calculate our inverse matrix, right? So if we're to start this process here, then what we end up with is, by multiplying the first row by 2 and subtracting that from the second row, we get here. But now notice how on the left side we have this, which is showing that the first column, or the first variable, let's just call it x1, can be expressed in terms of x2, or our second column. And our second column has no limitations on it, right? So we can treat it as some placeholder or parameter variable t, and t can take on any value. And accordingly, we get infinite solutions, right? So this is just one example, but in general, if the columns of a matrix are such that the first column is a scalar multiple of the second, or really any scenario in which one column of a matrix is a scalar multiple of another column of the same matrix, then it is not invertible. And that's exactly the situation that we have here if we allow the determinant to equal to 0. If you found this content informative, please support the channel by liking this video, sharing it with your network, subscribing to the channel, commenting on a video. Any way that you would be interested in supporting the channel, I would appreciate your support. Further, if you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.